Welcome back, everyone. So the last time we finished review of prerequisite material, and we defined limits and continuity for multivariable functions. We proved a couple of propositions, or at least I proved one of them, that a limit of a vector valued function exists if and only if the limits of each of the components exist. And I also stated the sandwich law and sketched a proof of it. Okay. Here are some examples of limits. All right. So suppose the limit of x1 goes to a1, g of x1 is b, where g is a one variable function. Okay. Then if you treat it as a several variable function, that is x vector goes to a vector, g of let's maybe call it f of x vector, this is also equal to b if f of x vector is this one variable function. Meaning, if you take a one variable function and you pretend that it's a function of two variables where it doesn't depend on the second variable, then this multivariable limit is indeed equal to the one variable limit. Might sound a bit obvious, and the proof is also not difficult, but the point is you will see how subtle multivariable limits can be in just a moment. Okay? Right. So how does one prove this? Well, so given epsilon greater than 0, there exists a delta epsilon greater than 0 such that whenever is less than delta epsilon, and of course x1 is in the domain of g, mod of g of x1 minus b is less than epsilon, right? Now this means whenever 0 is less than x minus a is less than delta epsilon and x1 is in the domain of g, f of x minus b is less than epsilon, right? Why? Because this implies this. If the full norm of the vector x minus a is less than something, so is each component of this vector less than that, right? So this is very straightforward. So in particular, what I mean is limit as xy goes to 0, 0, sin x equals 0, because it's a one variable function. Now I'll just show you how subtle multivariable limits can be. The limit as xy goes to 0, 0, xy divided by x square plus y square does not exist. Okay, so since this is our first genuinely multivariable example, I'll do it in some level of detail. So first of all, what is the set S on which this function is defined? It is R2 minus the origin, right? It certainly makes sense on R2 minus the origin. Okay, so that's I need to tell you what the set S is on which the function is defined. This is very important, because if I don't tell you that set S, the definition of a limit doesn't even make sense. Also, you have to be very careful. On paper, I can take the same limit. It could fail to exist if I change the domain of definition. Okay? And it could exist if I don't change the domain of definition. I urge you to come up with an example of this on your own, of this phenomenon where the domain makes such a big difference in the limit. Okay? Normally we won't state the domain because it's understood as to what the domain is, but it's important, right? Right. So why would we naively expect it exists? Notice if we fix y, right? If we fix y to be equal to 0, let's call this function f of xy, f of x comma 0 is identically 0 for all x. So the limit as x approaches 0, f of x comma 0 is 0. Likewise, if we fix x equals 0, the limit as y approaches 0, f of 0 comma y is also 0. So naively, if you fix the variable x and you take the limit in the other variable, that doesn't help. Like for example, even if we fix y to be not necessarily 0, even if we fix y to be say non-zero, f of x comma y limit as x goes to 0 is still 0, right? Why? Because if you fix y, you take x goes to 0, this goes to 0, this goes to y square, which is not 0, and so by the usual limit laws of one variable calculus, this goes to 0. So taking a multivariable limit one variable at a time is a terrible idea because it will give you wrong results. In this case, if you were to have naively done this one variable at a time, you would have been in very big trouble because this limit actually doesn't exist. Why does this limit not exist? I'll give you the rigorous proof in a moment, but the intuition is as follows. And this intuition can be made rigorous in a very nice way by means of a theorem I'll state soon. But the intuition is different paths give different limits. What I mean is, if y equals x, then f of x comma x is x squared divided by x squared plus x squared, which is half. When y is 2x, what will you get? You'll get 2x squared divided by x squared plus 4x squared, which is 2/5. Right? So if x and y get closer and closer to 0 along this line as opposed to this line, you get different numbers that don't agree with each other, and therefore the limit doesn't exist. This is very similar to taking left hand limit and right hand limit in one variable calculus, right? The trouble is, in multivariable calculus, there are infinitely many ways to approach a point. Not just from the left or right, you can approach it like this, you can approach it via a straight line, you can approach it via a sequence, and so on and so forth, right? That's the trouble, okay? So how does one make this rigorous? Well, one uses contradiction. Suppose this limit does exist, exists and equals L, some number L, okay? What this would mean is f of x can be made very close to L, in particular 1 by 100, if x is very close to 0, right? So in particular, if y equals x and x comma x minus 0 comma 0 is less than delta, that is maybe instead of this, so this would mean that square root of x is less than delta, so x is less than delta by square root 2, then f of x comma x minus L is less than 1 by 100. What is f of x comma x? It's half. In other words, L is very close to half. If y is 2x and 0 is less than x comma 2x is less than delta, that is if x is less than delta divided by square root 5, right? Then f of x comma 2x minus L is less than 1 by 100, that is 2/5 minus L is less than 1 by 100. So in other words, if mod x is less than delta by 100, for instance, then we can conclude two things at once, and 2/5 minus L is less than 1 by 100, and this is a contradiction. There's no way L can be 1 by 100 close to both half and 2/5, right? Why is that so? Because if, well, that's just the triangle inequality, but you can also see this numerically, right? So that's the point. Okay, so right. That being said, here is one more interesting point. If you take this limit, this does exist. Let's assume that this domain of definition is R2 minus the origin and equals 0. So a function that looks very similar to the previous function does have a limit, right? You have to be extremely careful here to not prove this by merely taking two of your favorite paths and seeing that they give you the same answer. Using two different paths to approach that point and getting different answers will show that your limit does not exist. It can never be used to show that the limit does exist, because there are infinitely many ways to get to that point and your two favorite chosen paths may not be good enough. Yeah? So this has to be done carefully. Now the point is x square y square by x square plus y square is larger than 0. Yeah? It's less than x square itself. Why? Why? Because y square divided by x square plus y square is less than y square divided by y square, which is equal to 1. Okay, so x square times this is less than x square. Now as xy goes to 0, 0, this limit exists and it equals 0. Why does it exist and equal 0? Because this is a one variable function and the one variable limit exists and equals 0, and therefore by the proposition we proved, or rather the first example, this is 0, this is already 0, so by the sandwich law, this is 0, this goes to 0. Okay? So you would have to be a bit ingenious in dealing with these things, but not to worry, we will come up with lots of strategies to do limits. Okay? So the following theorem allows us to directly conclude non-existence without going to deltas and epsilons using two different paths. So first of all, we define convergence of sequences in the usual way. Convergence of sequences, we have already done this. Recall the definition. Okay, we have already defined this in more than one variable. Now the point is, the theorem is as follows. Suppose this limit xy exists and equals L. If xn goes to A and yn goes to B such that xn and yn lie in the domain of f for all n, then this limit exists and equals L. In other words, if a limit exists and equals a number L, then for every sequence that limit exists and equals L. So if I choose two different cleverly chosen sequences that approach different numbers, for which f approaches different numbers, then I will have proven that the limit does not exist, right? So how does one prove this? This is again not rocket science really. So what does it mean for the limit to exist and equal L? Given epsilon greater than 0, choose delta, which depends on epsilon, such that whenever such that whenever whenever delta is right, sorry about that. Okay, so I'll just state it out loud before writing. So whenever so what does this mean? Whenever delta is small enough, yeah, and xy is delta close to a comma b, and xy lie in the domain of f, obviously, right? That means this f of xy exists and it equals and f of xy is epsilon close to L, right? Now xn goes to a and yn goes to b, which means for sufficiently large n, for all n large enough, xn is delta by 2 close to a, right? Likewise, if n is sufficiently large, yn is delta by 2 close to b, right? So if n is so large that both of these happen together, that is xn is delta by 2 close to a and yn is delta by 2 close to b, xn comma yn will be delta close to a comma b, right? Why? Because the distance between these two is square root of xn minus a square plus yn minus b square. If xn minus a is less than delta by 2, yn minus b is less than delta by 2, then the square, the xn comma yn is delta by square root 2, in fact, less than is xn comma yn is delta by square root 2 close to a comma b. So as a consequence, f of xn comma yn is epsilon close to L. It's very straightforward, this proof, but this little result is very useful because we could have using this result, we could have proven the previous example, this one, much easier, right? So this intuition of different paths giving different limits can now be made rigorous, right? Simply choose one sequence to be 1 divided by n, comma 1 divided by n. As n goes to infinity, this approaches 0, 0. Choose another sequence to be 1 divided by n and 2 divided by n. As n goes to infinity, this sequence also approaches 0, 0. However, f of 1 by n comma 1 by n equals half. F of 1 by n comma 2 by n equals 2/5, right? So in other words, we get two different limits, and therefore by this theorem the limit doesn't exist. So we don't have to worry about deltas and epsilons anymore. One more important point, right? This theorem which is useful for non-existence, namely this one, this is applicable for functions of more than one variable, more than two variables as well. Okay, I have stated it for two variables simply because it's easier for you to grasp this point, but this is a general theorem. The same kind of a proof works. So even for multivariable functions, more than two, even if you have 3 variables or a billion variables, if you have two different sequences going to the same point, but the values of the functions approach two different limits, then the limit doesn't exist. Okay. All right. So now we have lots of ways to prove non-existence of limits. Proving existence of limits is still a complicated affair, right? We have the sandwich law, and if your function is simply a one variable function, you can simply write the limit, but otherwise how do you prove existence for limits, right? So you have limit and continuity laws, right? So you have limit laws. So limit laws, these laws are very similar to the laws we use for one variable limits, right? So so suppose f and g are two functions. They could both be vector valued functions. So if f and g are two functions, then and let's say their domain of definition is the same. Okay, right. So the first one is the following: if the limit of f exists as x approaches a, right? As x approaches a, if this limit, by the way, as I said, I'll stop putting the vector valued signs very soon. So suppose this limit does exist. Okay, let's call the limit as b. Right. And likewise, if the limit of g also exists, right? So if the limit of g exists, and let's call it c, right? So the first step for the first property, if you wish, is that the limit of the sum of these exists, and the sum of the limits is the limit of the sums. So in other words, if you take f plus g, this limit exists and this converges to b plus c, right? Right. So this is the first property. We'll prove these properties soon. It's not very difficult to prove these properties, but the proofs are very similar to their one variable counterparts. Okay, just like the results are very similar to their one variable counterparts. So the second one is also similar. It's not shocking. If you multiply f by some scalar lambda, right, this limit exists and it converges to lambda times b, right? So if you scale the function, the limit also scales, right? Likewise, if you take the dot product of these two vector valued functions, right? If you take the dot product of these two vector valued functions, this limit exists and it goes to whatever you expect it to go to, b dot c. So in one variable, this would a special case of this. Suppose these were not vector valued functions. Suppose these were scalar valued functions. What this is saying is, if you multiply two scalar valued functions and you take the limit does exist and it equals the product of the limits of each of these scalar valued functions. This is a generalization of that point. Likewise, the fourth property is that the limit of the norm of f exists. The limit of the norm of x exists as x goes to a, and it goes to the norm of b. Okay. So the limit of norm of x exists and it goes to the norm of b. This is to be expected, of course. For example, f dot f is the norm square, and the previous property tells us that the norm square of f goes to the norm square of b. So it's not shocking that the norm of f goes to the norm of b. Right. So we'll see that this operation of taking square roots, preserving limits, that will also follow in a moment. Right. So suppose f and g are now scalar valued, they are not vector valued, and if g is not 0 in a neighborhood of a intersected with s. So I want to talk about f divided by g, right? So if I take f divided by g, I want to say that this goes to b divided by c, right? The only thing you need to be a bit careful about here is that g, first of all, obviously c must be non-zero for this to make sense, right? So if this happens, then f divided by g goes to b divided by c for if the limit is non-zero, right? You have to be a bit careful whilst talking about this, because f divided by g need not even make sense on all of s, right? So, this raises a small little point. If you take the limit in multivariable calculus, limit as x goes to a f of x, this limit, its existence or non-existence depends only on the behavior of the function in a neighborhood of a. What does that mean? You can prove this for yourselves. This is an exercise. So, suppose I have two functions f1 and f2, and let us say they have the same domain, right? And I take the limit of f1 as x approaches a, and let us say it is some value, right. Now, suppose we know for a fact that f2 agrees with f1 in a small ball around a, okay. So, the domains are the same. If you take a small ball around a, it intersects the domain in some set. Let us say on this set f1 and f2 agree, okay, no matter how small the ball is, okay. Just choose some, suppose there exists an open ball of some fixed size such that its intersection with the domain of f1 and f2 is a set on which f1 equals f2. So, in other words, f1 equals f2 in a small neighborhood of a. Then the limit as x goes to a of f2 is equal to the limit as x goes to a of f1. If the limit of f1 does not exist, neither does the limit of f2. If the limit does exist, so does the limit of f2, and they are equal to each other. In other words, the behavior of a function near that point, near the limiting point, is all that is needed to define a limit, right. So, please prove this for yourselves, okay. Please think about why this is true. So, as a consequence, f divided by g here, so here f divided by g need not be defined on all of S. Why? Because g can potentially be 0 on a large part of S. Regardless, the fact that the limit of g as x approaches a exists and it equals a non-zero number would mean that in a neighborhood of a, g is not 0. In a neighborhood of a intersected with the domain of f and g, g is not 0. Why is that so? Please think about it, okay. So, as a consequence, the function f divided by g genuinely makes sense in a neighborhood of a, and that is all that is needed to talk about this limit, okay. So, the bottom line is, throwing the disclaimers and the legal objections away, f divided by g does converge to b divided by c provided c is not 0, okay. That is all I am saying. So, nothing about this set of properties is shocking, because they are exactly the same properties that work even in the one variable situation, and as we will see, the proofs will also be similar. The same laws apply for continuity as well. If f is continuous at a, g is continuous at a, f plus g is continuous at a. If you scale a continuous function by a number, the resulting thing is still continuous. If f and g are continuous, their dot product is continuous. If f is continuous, so is the norm of f. If f and g are continuous and g of a is non-zero, then f divided by g is continuous, and so f divided by g is continuous, right. So, the same laws hold for continuity as well. We will prove these laws the next time. Again, as I said, the proofs are not rocket science. They are very similar to the one variable proofs, and then we will move on to differentiability, right. Thank you for joining. We will stop here.